Today I'm going to power through a lot of material today. Apologize in advance. See how well this goes. I'm going to start talking about trees, which is actually one of my favorite topics. And in particular, I use them a lot in my own research. And we're going to talk about trees that they're not exactly the best classifier or regression approach that can be taken. But I'm always talking about these two sides, one being predictive accuracy, one being model interpretation or inference. And when you want to make inferences, trees are really, really well suited for that. So I've used them a lot in my own work, and they're also going to be the base classifiers for some of the ensemble methods that we're going to talk about today. Okay, and probably next week. We'll see how far we go. Okay, so what is a tree? Okay, we're going to start talking about some real-world problems. I really want to try to motivate this well. We'll talk about growing and pruning, which is exactly what it sounds like, you know, if you're thinking about gardening and so forth. Metrics for deciding how to do model selection, because again, this is a machine learning method. We need to do some kind of selection. There are going to be parameters that are involved. I'll give a couple examples. We'll talk about visualizations and some conclusions. This is really just the tip of the iceberg. Okay, so I'm going to power through this. There's about 60 slides or so. We'll take a very short break, and then I will tell you a little bit about, we'll end this talk talking about my conclusions, why trees are really bad, what's wrong with them, okay, and why it will motivate the second half of this class, which is going to be a discussion of what can we do to keep using trees but to make them a little bit better, okay? So that's the plan. Okay, so this is actually a book I have on my shelf. It's an old book, and so these have been around for a long time, and they've been motivated largely by medical examples. And in fact, in my own work, and I've published in this domain, using them to analyze data for people in pharmacology or looking at toxicology data, medical decision making, they're huge. Okay, so why? Well, they're really easy to interpret. It actually mimics, you know, a doctor's thinking or a practicing physician, whatever, is thinking in that domain. Okay, just asking a series of questions to try to come to some conclusion. That conclusion could have an outcome that is either classification or it can be regression. Okay, so this is a motivating example. You want to predict high-risk patients who will not survive at least 30 days on the basis of 24-hour data. There's 19 variables that are measured here in the first 24 hours. They include blood pressure, age, etc. Okay, not so important what's measured, but there's 19 things that are measured. And we're trying to predict high and low risk, so it's a classification problem. So you have tools to do this, right? I mean, you can do things. You know, I see probably can't use Gaussian assumptions depending on what some of the things are, but you know, you can do a logistic regression model. You can do KNN. You can do other things as well. So why a decision tree? Well, let's just take a look at what it looks like. This is the result, and what you're going to see are nodes. And for those of you that have taken 546 or that are going to be taking 546, you're going to become very familiar with this type of structure. Okay, this is a graph. The nodes represent variables, biological variables, or decisions. In this case, is the minimum systolic blood pressure over 91? Okay, so this is the question that's being asked. If it's not, then they're high risk. Okay, so if the blood pressure is really low, probably you're going to die in 24 hours. I don't know. This is what it's talking about, whatever that risk means. If it is, then you need to start asking a little bit more, okay? Because blood pressure is just not enough to make a decision. It's only one of the variables out of the 19. So you move to the next question. What's the age? Is it greater than 62.5? If it's not, then they're low risk, okay? If it is, you need to ask another question, okay? Is sinus tachycardia present? If it is, high risk. If it's not, low risk. So this is exactly a process, and actually you could think of this even as a sequential process. So when I take my son to the physician, they do some blood work. Geez, his iron levels are really low. We need to do a little bit more testing. They do additional testing, okay? Well, if the iron flag didn't come, additional testing might not have been warranted. Maybe then they have to do some kind of diet intervention or vitamin therapy, okay? So these are the kind of sequential questions that one might ask. In this case, the sequence is not necessarily interpreted sequentially. It's a full data set. But if you're thinking to yourself, what if this is the model I want to use? What if this is a model, it's in the computer, and I want to kind of predict, here's a patient coming into the ER, and I need to kind of understand, well, these are going to be the key things that we're going to be looking at, okay? But guess what? There's only 3 variables represented here out of 19, okay? I didn't tell you what all the 19 were, but there are 19 features in this data set. Okay, so this is one of the interesting things about classification and regression trees, is that there is an inherent feature selection piece there. Okay, not all of the variables are guaranteed to be picked up. Moreover, features can be picked up more than once in the same tree. So if this was a rich tree, I might see age further down the line again, maybe a different break. Are they less than 20, right? So that's the kind of thing you can think of. And this is also having an interpretation that is somewhat hierarchical, okay? I can tell by looking at the ordering of the tree what the most important features are down to the less important. And then those that are not there are just not important. So this is a very useful practical thing. This is just another example. I'm just going to skip through it. Of the same thing. You can look at it on your own. This is what this looks like if you had 2 features, because we want to visualize things. So what's being done? Binary questions are being asked, and those binary questions divide the plane or the feature space for that variable, the range, into 2 regions, right? You only had 2 branches coming out of each one of those questions, right? It's yes or no, yes or no, yes or no. Okay? So that's the point. And so, those are categorical variables, but of course we could have continuous variables, and then it's really easy to kind of understand this feature space. So what we have going on then, in this example, is price of a vehicle. It's somehow standardized with respect to horsepower and wheelbase. Okay, so 2 measurements on a car. And this is just a contrived example. It's not even, I don't think it's from your textbook, but I grabbed it from something else. So we have these different features here, and they're plotted. And what you see is that here's the first split. It's on horsepower. This is the most important of the 2. And we're going to kind of move things. I have to split it at one point and push everything to one side, push everything to the other. So here I am, I've got horsepower split, and I can kind of see, in this case, it looks like it's kind of over too far in this picture, but we have a line here, which is dividing the space. Okay, it's just dividing the space. It's nothing fancy. And you're going to see that the actual search is absolutely nothing fancy. Now that I've done that, I need to search within these subregions. Okay, and so the subregion would be everything to the left and everything to the right. And what am I looking for? Well, I'm looking for points that separate different types of prices, okay? And I'm going to make this more concrete in a minute, okay? But this one says, well, you should split on horsepower again, okay? And so we can split on horsepower again. And this one says, well, you can split on wheelbase, okay? So we're just kind of drawing lines, and we do this all the way. Now, this is a regression problem. And, of course, there's repeated presences, because there's only 2 features, and I got a rich tree of horsepower, right, and wheelbase, both. They're in different spots in the tree. They're both present. But I have different price categories here. Okay, so this is the classification at high or low risk. But I have these features, which are saying that, well, if I land in this terminal bin, my price is going to be as that. Okay? And this price is derived very simply. It can be done in some different ways, but for our purposes and for the most often used approach for getting that y hat is just to take the average of training points in that region to determine the price. So a lot of things going on here. These are called terminal regions, okay? And they're populated in this model space, which we can visualize here. Generally, we can't visualize such a space. And what is the point of such a thing? Well, this is all our training data. Now, if I take a new data point here or even here, it's even better to think about. A new patient comes in, a new group of patients, and I kind of think about sprinkling them at the top of the tree and seeing where they fall. Okay? So you're going to have patients or automobiles coming into certain ranges. Okay? And that's going to give you your y hat. That's how the testing is done. So it's just simply tracing things down the tree, ending up in certain regions. Some things to think about. Another subtle point that's very important is that somebody is labeled as high risk. Well, there's different ways you can be high risk for something, right? And so if I say, well, you know, I ended up in this bin, okay, I have an impression of why that's true. It's because of this path, okay? And if I end up in this bin, it's strictly because I'm, you know, my blood pressure is of a certain value. So I can interpret, this is a terrific interpretation mechanism. First of all, I've mentioned to you that we have the important features. There's inherent feature selection. We have multiple ways you can be high or low risk, and you can kind of trace the reasons accordingly. And we understand by the hierarchy of the tree what the most important variables are. So these are the major points. So one, for example, quiz question I could ask you to do is to think about taking a data point. This is a tree, right? Taking a data point with these different measurements and telling me what the prediction is and what the terminal region is, and maybe just describing some of these advantages and disadvantages I'm talking about right now. Okay, that's a very important point. Okay, so let's talk a little bit of mathematics now. We're going to denote the feature space, in this case, by chi. The input vector is an element of the feature space. Okay, we're going to assume that we have p features, okay, which are just variables in our X matrix. The language is just going to change a little bit, and I'm also being consistent with the language in your book. You're going to see this a little bit here. Some of these may be categorical. Okay, that's not a problem. We can deal with categorical data. Okay, so tree structure classifiers, or regression models, are done by using repeated splits of the subsets of the feature space, X chi, into descendant subsets, beginning with the feature space itself. So what does this really mean? It's exactly what I kind of said. You have a feature space, and you're dividing the feature space, okay? And you're splitting it in such a way that your next split is conditional on what just happened, right? Because when we show that picture, we kind of say, okay, well, we divide this, and then we have to ask the next question, and then the next question. So it is a recursive process, okay? But it's very straightforward. So some terminology that you're going to hear and read about in the book. You've got node, terminal node. This is one that's going to be important. Parent node and child node. Again, you're going to see these things again in 546 when we talk about graphical models. Parents and children. Now, it is true in this case, because of the splitting of the variables, xj, in the feature space, that the union of the children is equal to the parent. Okay? In other words, we can't just take one piece of the feature. It's going to be the actual union. Now, when we get to random forest, the game is going to change a little bit when we talk about categorical features. But for now, we're just doing splitting of the feature domain. Every leaf node or terminal node is assigned a class. And a prediction is associated with the class that the leaf or terminal node, the subject lands on, okay? Which is exactly what I've said in words so far. Now, we're going to have a little notation here. A node we're going to define as T, and we've got the left and the right children nodes, okay? TL and TR. A collection of all nodes is defined by T, and the collection of all leaf nodes by T twiddle. We're going to call splits S, okay? And the set of splits as capital S. Okay. So let's talk about a visualization. This is, again, a two-feature piece. And what this cart method is going to do, there's only two features again, so we can visualize. It's going to scan over x1. It's going to scan over x2. That's a poor name for the variable anyways. In this case, maybe we'll call it z1 and z2. But it's going to do a splitting here of this featured domain into region x1 and x2. Okay? Now, this thing is stuck here. Okay? There's nothing we can do. That was actually the best split that could happen. Okay? And I'll talk about what best split means too. This is just a warm-up. So after I have that black mark in there, I need to determine what other splits I should make. Well, I'm finding that I can split this way, okay, because I have to consider this subspace and this subspace separately. I split here, okay, which is what I see here, and I make a third split here. Now, it's not necessary that I made a split from each of these parent nodes. I could have just said, well, this one doesn't really work, right? Just looking for good splits, okay? Then once I have these splits, I need to carry this tree through. This is conditional, and I need to look. Now I'm going to search in each of these regions for other split points I can make that are going to fit the training data well. And in this case, there's one more split to be made here, okay? So that's the idea. And it is really described, the way I'm describing it is exactly this divide and conquer idea, okay? You're partitioning the feature space into subspaces where the models and the interactions are manageable, okay? So we're just making this a really, really simple problem by doing this subspace splitting. And this is true despite how many features we have, okay? I mean, things get kind of messy when we have massive, massive features. This is also can be computationally intensive, but it is still manageable for large P. Decision tree. These decision trees use this, what we're going to be calling recursive partitioning. It's recursive because it's depending on the layer above it to subdivide the space until simple models can be fit. And what are the simple models? There's two of them. If it's regression, it's just taking the average of the terminal region. If it's classification, it's taking the majority vote, okay? So in other words, I've got all disease in this class, and I'm going to be called as having disease. Or if I'm, 70-30, I'm going to go with the 70%. So it just depends on the proportion of points in that terminal region that have a certain label. Now, what I'm alluding to here about majority vote probably has your wheels turning about how do we actually decide where to split the data, okay? We're coming to that, okay? All right. Now, in terms of nomenclature, and when you go to the computer, you're going to see things like this. First of all, you have your data set, and you have your decision rules, okay? And you have to divide the space, okay? Also would be a very good exercise to do in a quiz. So we have here the first decision rule, for example, is T1. So you should be able to take this information and draw the splits, okay? I would give you values for these, but in this case, it's just, So X1 is split again, so we have kind of this another split here, okay? When X2 is equal to T2, this is the next split, When x1 is greater than t1, we're going to split at what we call t3, okay? And we're going to split again at a t4, okay? So that's what that would look like. So actually, what you're going to have to do in your homework is to be able to interpret these rules. Of course, in this particular case, it's easy to visualize, but in general, you're not going to be able to draw that. So that always causes mass confusion, okay? But this is what's happening, okay? Another way that we can write this is to write it as the decision tree. So these are three equivalent ways of representing a cart model, okay? You've got the information about the splits, you've got this partitioning of the model space, and you've got the tree itself. Okay, these all go hand in hand. In practice, although we think about things in this domain, we usually can't draw it in this domain. So we have the decision rules coupled with the tree. Now, if I was to make my final prediction, right, what's my y hat or what's my f of x? In this case, it's going to be the average of the terminal region. So this is going to be over, in this case, there's five terminal regions. Okay, so it's going to look at those points and where they fall into and look at kind of the majority vote if it is classification or the average if it's regression. Okay, so let's give some advantages, which I think are pretty important because there's so many disadvantages, so I really try to motivate these positive things about the trees as well. It's very fast, right? So if somebody new comes in, I'm going to just push them through the tree and that's it. The important variables fall out. Okay, when data is missing, we can carry out interesting calculations on different branches that are still informative. This is a really powerful property of the trees, which is a sneaky thing that a lot of people are not really familiar with. But this is one of my motivators on certain occasions for going to trees. It has a very interesting way to deal with missing data, okay, without having to discard the observations. If the true regression surface is non-smooth, the regression tree will provide a non-smooth response. And this is true, of course, because of this nested, these layers of the graph can also be thought of in terms of interactions. Okay, interactions with the previous layer. So from that point of view, we can kind of capture some of these nonlinear aspects. And likewise, if it is smooth, we can also get a good approximation. It's really fast to do, surprisingly. Now I want to relate it to clustering. And this is one of the first things that I do when I think about the trees. Okay, so some of you haven't studied clustering formally. You will study it next semester with me if you stick around. But in clustering, what we're trying to do is maximize information, make groups really tight, right? And regression trees, we're also trying to maximize information. In particular, with respect to y and which variable or which leaf, the tree, and the tree that we end up on. What does this mean? Okay. So in clustering, there's two objectives. So whenever I ask somebody, what is the major objective of clustering, which I tend to do a lot, because it kind of escapes people in the complexity of how many different methods and different things we can do with clustering. But the objective is to make really tight groups of things that are similar and to be sure that those groups are well separated. So you're searching for groups that are very close to each other, but very far apart from other groups. Okay, so that's the idea. And actually doing this is no different. We're searching for terminal regions in a way that are very similar to each other. So when we want the training set, we're trying to find groups in that feature space that are very similar to each other, whether it be their class label, if we're in classification, or their value, if we're in regression. Okay, because that is what we want. That's going to provide really good support for my new predictions or my test data that's coming through the pipe. Okay? All right. So that's the idea, and I think I've said this already, so I'll just keep moving. All right. So how do you grow a tree? There are three elements to it. One is the selection of the splits. Okay. What does that mean? Okay. Well, it's really actually kind of easy to think about. I mean, if I asked you, again, what's a logical way to solve this problem? Let's say I have an x1 and an x2, and I have different classes here. One thing you might say is that, well, I need to kind of scan through x1 and at all these different split points, evaluate how pure the TL and the TR, the left and right child node, the candidate left and right child node, how pure those nodes are going to be. Okay? So in other words, I'm searching for that S in some kind of sequential way, scanning, and I'm trying to find that S that's going to give me the best separation between the classes. Okay? So that's the idea. So I'm searching in this way, and then I'm going to scan x2, and then I'm going to scan x3, and x4, and x5, and I'm just going to keep scanning and scanning and scanning. And one of those is going to produce a good split, or you can at least rate them, right? So in a way, the selection of splits also relates to, it's a search over the features as well, okay? The other thing that comes into play is when do you stop? I mean, you can grow and grow forever, right? We can just keep splitting the feature space, and so actually once I scan through, let's say I find x2, I'm going to split x2 at 50, okay? Now my next search is going to be conditional on the fact that x2 is split at 50. So now I've got two regions to search over and those variables accordingly, okay? So it's going to keep going on and on like that. And so as I grow this tree, it becomes more massive, There's more terminal nodes at the end. And if I think about where my training data is ending up, my training data in those terminal regions is going to get smaller and smaller and smaller. Okay? Because there's more spaces that this training data is going to sprinkle down. Okay? If I have just a stump, then we hope we have a 50-50 split or something close to it. Let me try this. Okay, we reset it. Let's see. So yeah, we hope that that's true. But if we overgrow our tree, what ends up happening is that we end up with poor support in a region. So in other words, if I have this simple tree that I keep going back to, and I only have 10 patients to fit this model, maybe I only have 2 that end up here, right? Well, yeah, so if I go out and get a new cohort of patients and sprinkle them down the tree, and I'm calling those people high risk, there's not a ton of support in the data to call them high risk, okay? Because the terminal nodes are kind of starting to spread thin. This is a contrived example. You wouldn't build a tree like that in this case, but you'll see some richer trees that will happen for. So we'll talk about these decisions, okay? And finally, you have to assign a terminal node to a class. That's actually the easiest piece, okay? All right, so this is going to distract me, so just give me. So I've already talked about doing the model prediction within the region is very straightforward. We're just looking at the points over a particular region and determining what the majority should be or the average. Okay. So what are some of the points that you should also be aware of? They're easy to interpret. They have an if-else type of nomenclature. You can't draw them, at least the feature space, in multiple dimensions, which is unfortunate. And of course, I've already mentioned it mimics the doctor's thinking. It's very popular in medical science. Okay. So the data, of course, is going to look like our same data that we've been using all along. Okay. And we want to do something automated. Okay, so now we're going to think about formalizing this, partitioning the space into M regions, R1 to Rm, and the response is modeled as a constant. We're going to call that constant Cm. And if we use residual sum of squares for a regression for the loss function, then what we will have is just the average in the particular region. So a lot of these things I've said in words already. One can think of this as a greedy approach, okay, because it is this divide and conquer. And we're starting with all the data, and if we formalize this with respect to the splitting, you're developing two regions at a split point, and it's conditional on what happened beforehand. And these two regions are simply asking these binary questions, and they encompass the entire domain of xj, the splitting variable. The splitting variable j and the split point s will solve this equation, which is looking for the points that are going to minimize. In this case, it's written as residual sum of squares. Okay, but we just talked about purity and impurity. It's the same concept in classification. We want the proportion of points of a certain class to be well represented and high in these different regions. So it's going to actually search simultaneously in just the way I described for the x, the xj, and for the s. Okay, so the two things have to be found together to solve this problem. And then once this is, decided upon, the inner minimization piece here is just the average. Okay. All right, that's just okay. So let's talk about when to stop. I've already kind of described it. It's very simple to do this splitting. It's intuitive too. If you split too much, we have a lot of regions with a few data points. That's going to be obviously overfitting. We're finding subsets that are too small. However, small trees may be too simplistic. So we want something that kind of goes between. And think about what we have done in the past. Right? We've always had this issue where we think about overfitting and underfitting. We try to find something in between. We try to find this minimum and that generalization error. Well, the same thing is true, but we want to do that somehow with respect to this tree growing algorithm. And that's actually not so straightforward because what are the complexity parameters? There's really not any. I mean, we're going to grow the tree, but it's going to become the error is going to go down, 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 just like the training data would in that curve. One could set aside test data and think about monitoring that as well. Okay, but we're going to describe a few alternative approaches that work quite well. And again, it's intuitive. If you think about, if I asked you what to do and you didn't know any better, you would say grow it and then just cut it back. Okay. Obviously, that's not a super clean idea, right? I might argue with you that, well, I mean, it seems kind of stupid to just grow this thing super deep and then, I mean, why not just track it and figure out when to stop, okay? But that question is actually not very well resolved, okay? So the best thing that we can do is this tree pruning, which is kind of, to me it seems very clumsy, but it does work in practice. So we're going to grow a large tree, and we're going to do that until the terminal nodes are pure or close to pure. So just grow it deep. It doesn't matter to me how many things are in the terminal nodes. We can do this, for example, until we can give a threshold. We could even say we want one item in each terminal node, which is ridiculous, right? So that means you have one training point of support in that particular path, okay? Or you could say 5, or you could say something else. It turns out that as long as the tree is large, the size of the initial tree does not matter very much because we're going to cut it back. Okay, so it's better to go deep than to go too shallow and do the pruning from there. Okay, so that's actually the moral of the story. Okay, so how do you prune a tree? Well, again, we have this idea of descendants and ancestors. Okay, ancestor being the opposite of the descendant. You got the parent node and the children, or the children and the parents, however you want to discuss it. But you can kind of imagine what a branch is. So when you go out and trim a tree in the backyard, you're just snipping branches. And the same thing is true here. Okay, but when you snip a branch, this is just a bunch of jargon and notation to say that when you snip a branch, everything in that branch goes. Okay, so how do you decide how to kind of prune this tree? There's lots of different branches you could snip at. You could snip at different parts. Maybe you just want the end of the branch, or maybe you want to take the whole thing, right? So that's the idea. And when you prune a branch, you know, this is just saying everything falls. And you can denote that tree by T minus T subscript T. Okay. And T prime is obtained by successfully pruning off branches. It's a subtree. So once you prune the branch over here, you might want to prune another one, and so forth. Okay, so this is a tree in its full size. Maybe it's grown sufficiently deep. And, you know, this is a branch. Okay, so this branch is over here. Okay, and if I want to look at this tree without this branch, it looks exactly like the tree without the branch. Nothing mind-blowing here. Okay. However, if you think about enumerating all possible subtrees and combinations of taking off different subtrees, it's a hard problem. Okay? So how should we do the pruning? Okay, so one approach that your book covers is to do what's called cost complexity pruning. And again, it's not intuitive. You don't think, well, let's overfit the model and then cut it back. Okay? So we're going to let T, an element of T naught, be any tree that can be obtained by pruning T naught, the original tree. And so there's a couple things here to think about. One is the number of points in a terminal region, that's big N. And it has a subscript M, which corresponds to the terminal region that it's in. And we have our prediction in that terminal region, which is our C hat. Okay, that's what we've been calling it here. We usually call it Y hat, but here we're calling it C hat because it has that constant flavor to it, and I just want to be consistent with your book. But that's our prediction, okay? Whether it be classification or regression, that's what we have. And it's specific to the region. And now I have something here. This is called an impurity measure, okay? And what is it? Well, it's actually looking at the impurity. In this case, it looks like it's quantitative. But this can be shuffled in as something else too. Okay, it's just a measure of fit. And it looks a lot like the residual sum of squares, right? Because C hat is our prediction, and we're kind of looking at how far away that is from our true Y. Or in the case of classification, it would look like a misclassification rate in that particular region. Okay, so these are what we're calling impurity, because the larger it is, the worse off you're going to be, right? If I have a subspace that's not describing this region well at all, then it's quite bad. Likewise in classification. So I want to think about that, okay? And so what you're trying to do here should look very similar to what you've seen before. You are trying to minimize what we call this cost complexity criteria. And this is a function of the following, okay? And it goes over different, this is the cardinality of the subtrees. This is denoting the number of terminal nodes in the tree. So it considers all terminal nodes. And it's searching in a way that it's looking to minimize this. This is actually the impurity. We want to minimize the impurity. Think of it as a loss function. You want to minimize the loss function. It has the same flavor as a loss function. It even looks like a loss function. They just talk about it in a different terminology. But it is a loss, right? It is an impurity measure. And now what's this? Okay, so I just said it's like a loss function. Well, what have we been tacking on to loss function? Penalties, right? We've been tacking along penalties for a while now. We've done it with the lasso and with the ridge, with all those penalized regression discussions. We said we could do it with logistic regression. And what are we penalizing for? Model complexity, right? So it's a very interesting process because first we're saying, I don't care about model complexity. I'm going to grow the tree as deep as I can. But then when I go to the pruning, then I start to care, okay? And I start to say, well, we need to think about model complexity and overfitting. And that's exactly where this term comes into. Alpha is, like we have seen before, a tuning parameter. Okay, and the tuning parameter can be identified using all of the methods that we've discussed. Okay? All right, so here is this is a example from your book. This is a spectrum of different trees with different, this is for a single alpha. We're going to talk about ranging alpha in a minute. But what we're seeing here are the cardinality of the prune tree, kind of starting from more complicated to more simple. Okay, and so that's kind of the progression is which you would go. And so the question is, how stiff do you make the penalty, and what subtree do you use? Okay, so how do you tune the model? And it's not going to take much to think about this. Okay. We're going to talk about it in the context of k-fold cross-validation, which we've covered. Okay. This is an issue that's going to come back to bite us really soon. Okay, stability. Okay. Now I'm going to talk about trees. I've already talked them up for almost an hour. I'm going to start to talk them down now. So one problem is that the structure, especially as you start to overfit the model, is very unstable. Okay? In other words, you can have cost criterion or loss functions that are very similar, probabilities of being in a tree, very similar results, very similar things, totally different structures. Okay? So that's a major issue. Okay? We also say that in terms of variance. You hear me talk about high variance of trees. When I talk about that, I'm actually talking about the variance of the structure itself. Okay? So we have a lot of problems there. But we're trying to use alpha, and we're going to identify a subtree from an original tree, okay, based on this information. Okay, so this is an example here. This is, I'm going to move a little bit for the examples between the two texts, elements and introduction. Introduction doesn't give any details about the methods, but your other one does, but they have great examples. So I'm pulling from both here, starting now. This is for baseball data. I forget if it's salary or hits or something like this. But anyways, we have a dividing point in years. Years is an important feature. Then RBIs, hits, walks, runs, lots of different things happening here. And then we have values here. And I think they relate to salary, actually, now that I'm thinking about it. But this is the full tree. Okay, this would be a full, rich tree, and it's kind of decided that we shouldn't go any further by whatever reasons the authors have kind of determined this. Okay. Now, like before, we can use k-fold cross-validation. So we divide this into different folds, and I forget what k is here. It's not really important. The importance is kind of selecting the appropriate tree size or the alpha value that corresponds to the given tree size. Okay. And so what this is saying, of course, here's our training set, and we know it's going to go down, 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 okay, as usual. If we were to hold out a test set, it would kind of look like this, okay, in this sense. So it's not a clear, beautiful picture like we like to see. I mean, it's not that the standard errors are really well separated like we like to see. So it's a little messier, which is good. This is real life. Cross-validation, it does track the shape of the test error. It overestimates the error, okay, which is fine too. But again, what we're trying to do is estimate what the appropriate tree size would be. And it would be a lot smaller than the one that is here. Okay, so accordingly, each one of these is going to correspond to a given tree size that we would use in the end. Okay, and so I don't have the final tree here, I don't think, but that's the idea. So this is for regression, and cart methods can be used in classification and regression. This is one. Actually, this is the first method that we've really talked about that is well suited for both. We've talked about using regression on an indicator matrix for classification, but we said there's a lot of problems with that, right? But this method actually handles both very well. And the methods that we're going to be talking about this week and next week and the week after all deal with both, okay? So we know that the loss functions for regression are not appropriate for classification. And since I said that the cost criterion function or the impurity function is just a fancy term for saying loss function, we have the same problem. So we have to think a little bit better about what to do. And if you were going to describe purity or impurity, however you want to phrase it, you would think about in classification the proportion of points in a terminal region of a certain class. Okay. So you hope that that would be high for some classes and super low for the others. All right. Loss functions that we can use for classification and regression. It's the same thing, but now it's called impurity. So we have this cross entropy or deviance. I'm going to show you a picture in a minute here. Misclassification error. So they're all dependent on these proportions. Okay. This is going to give a little bit more sensitive idea for how far